In this final video, I'm going to show how what we've been talking about applies to more than just the geometric area underneath the graph. And we're going to do this with kind of an intuitive example here. So I made up these numbers, so I have no idea if this is realistic, but it says here that suppose a race car can accelerate from 0 to 150 miles per hour in 5 seconds. That might be completely unrealistic, but let's say it can. So, new superpowered race car, I guess. So now it's asking how far has the car traveled during the 5 seconds that it accelerated. Okay, and so what they're given us here is a little graph that tells us for each of those 5 seconds how fast the car was moving in miles per hour. Okay, and so if you remember that rate times time is equal to the distance, right? So if you go like 60 miles per hour for 2 hours, then you get 120 miles, right? Notice that the rate and the time have to match one another. And in here I got miles per hour, and then this time is in seconds. Okay? So what I need to know is how many hours each of these seconds is. And then I can use this formula for each number in this table. So I could say at 1 second, and I'm just going to say, this is the best I can do, I guess. 15, we'll say during that second I went 15 miles per hour. During that second, for the second we went 45 miles per hour. For the third second, we went 90 miles per hour, and so on. And then using this formula for each one, I'm going to find the amount of distance it went during each one of those seconds. Okay, so let's see here. 1 second is going to be there's 60 seconds, so 1 second is 1/60th of a minute, and 1 minute is 1/60th of an hour, right? And so putting this together, 1 second is going to be 1/60th of 1/60th of an hour. And that would be 1 over 3,600 hours. So 1 second is 1/360,000th of an hour. Okay? So now, we're going to say that the total distance here, and this, by the way, we're going to look at this in a minute. This is kind of a graph of each of these times. This is miles per hour. This is seconds. So the total distance here, let's say, so I'm going to say for that first second we went 15 miles per hour for this much of an hour, a small fraction of an hour. And then for the next second we went 45 miles per hour for this fraction of an hour. And then for the next one we went 90 miles per hour for this fraction of an hour. And then I'll continue it down here. Then I went 120 miles per hour for this fraction of an hour. And then I went 150 miles per hour for this fraction of an hour. Right? And then you can multiply those all together. Now I did this. Oh, it deleted it. I had it all done. So that's okay. I'm going to just type this in then. So 15, and what I can do is I can just divide that here. 15 divided by 3,600 plus 45 divided by 3,600 plus, you know what I could do is I could just add all these up. 15 plus 45 plus 90 plus 120 plus 150, and divide that by 3,600. And what I get here is approximately 0.1167 of a mile. Okay, so I get a fraction of a mile, and if I want to know how many feet, I can just multiply that by 5,280. There's that many feet in 1 mile, and this fraction of a mile then would be 616 feet. So that would be an approximate value of how fast, this would be the total distance. This would be approximately what the total distance would be. Now, a good question would be is that an underestimate? Is that an overestimate? So maybe you can think about that for a second here. But if you look here, for this first second, I use 15 miles per hour. Well, this car is accelerating, so that's as fast. That's the fastest time that it went during that first second. So each one of these is going to be an overestimate because you're using, in a sense, the end of the second. You're using the speed at the end of that second as an estimate of the speed that it goes over that full second. Okay, so what we're actually doing here is we're actually taking a right-hand sum over to find the area underneath this velocity graph. So in other words, this is going to be a graph, and I'm going to draw a curve now, and it kind of goes like this, kind of connecting these up, and then it goes like that. So this is kind of a curve, and this is like y is equal to like the velocity with respect to time. So in a sense, this is a graph of the velocity, and what I did is for each second here, I used the right endpoint to make a square, or to make a rectangle, right? Because this is the second, and then the height of each of these rectangles is the speed at the end of that second. And then what I did is I added up these rectangles, didn't I? Can you see that? So to get the total distance here, I added up, this is rate times time over each second, and then it gave me a distance for that second, which was an overestimate of the actual distance that it went. Okay, and then I added those up, and that gave me 616 feet, which is an overestimate. Notice now, I could have done a left-hand endpoint, right, and I would have gotten an underestimate, but I also could have approximated here, especially after drawing the graph, what the midpoint of each section was. And that would give me an even better one. Maybe what you could do is just find the halfway point, like 7.5 seconds, and then halfway, average these two to find the halfway point between each one. And then you're getting, it might not be the exact midpoint, because averaging these might not be exactly what you would get when you go halfway, depending on the steepness of the curve. And if you notice, this curve actually is concave up, and then it turned concave down a little bit at the end, right? So there's an inflection point in there as well. And in fact, let me just leave it at that. So you could, in a sense, get an even better estimate here by maybe finding the midpoint. If you did the left endpoint, you'd get an underestimate. But if you found the midpoint of each one, that would give you an even better estimate. Okay, and that's probably the best you could do, because you can't divide this up into more rectangles. So, for example, I couldn't divide this up into 10 rectangles, or 100 rectangles. But if I could, and if I knew the speed at each of those sub-intervals, then I would get a better and better approximation, right, of the actual distance. And it's as the number of those rectangles goes to infinity, or the width of the rectangles goes to 0, gets smaller and smaller, then it becomes the actual distance that the car has traveled, which is the same as the actual area underneath the graph. Okay? So here we see something interesting, is that if you have like a velocity graph, then the area underneath the velocity graph is equal to the total distance that the car, or whatever, that the object has traveled during that time. So there's a relationship between the velocity, right, and then the total distance that that car has traveled. The simplest example is if you had a constant function. So if I go 60 miles per hour, right, for, let's say, 1, 2, 3, and we'll say for 3 hours, right, it'd be 60 times 3. 60 times 3 is 180 miles, right? And that's the area underneath the graph of the constant function. So area is total distance. So you can see this, that because of the rate times time formula, the rate is the height of this graph, and then the time is the width here of the rectangle, or whatever you want to call, whichever you want to call. But one dimension is the time, the other dimension is the rate, and then the area of the rectangle actually gives you the total distance. So the area underneath the graph gives you the total distance, and this constant function is actually this formula, right? That's the true distance that you go. So now, if the thing is changing over that time, let's say you go on a trip and your graph is changing, 1, 2, 3. It's the same here as far as it's the area underneath this graph. The area is still the total distance. Okay, it's just that we can't use this simple formula to find it, but we could divide this up into rectangles and estimate it by adding up the area for each rectangle. And that's exactly what we're doing with these sums. So the area, one way to think of this is if let's say this in general is a derivative. If this is a derivative function, the area, if the function represents a derivative, the area underneath the derivative is the total change in the original function, or it's the total change in the antiderivative, right? And so this is actually the relationship, why there's a relationship between antiderivatives and areas under curves, okay? Because the area underneath the curve of a function is the total change in the antiderivative of that function. And that's actually the fundamental theorem of calculus right there, and that's what we're going to see at the very end. We'll actually prove that theorem at the very end, okay? And so very cool stuff here. So you could have other examples, and I'm trying to think. I don't know. I think there's one on the homework that might have a leaking, fish tank is leaking or something. An aquarium is leaking, but the rate at which it's leaking is changing. So the leaking here is actually it's leaking faster and faster as time goes on, and you're trying to find the total leakage, the total amount of water that leaked out of the tank in a certain amount of time. Same idea, it's just that the rate of change is not the speed of an object, it's the speed at which the water is emptying the tank. And you can have it where the function maybe is not even with respect to time. So if you actually have if you have this axis represent distance, so let's say you're pushing an object in a certain amount of distance, and so this axis represents the amount of distance that you push it, and this represents the amount of force as you push it along, the amount of force being used, then the total area underneath, or the total amount, the area, let me just say the area under the curve is equal to the work being done. Because if you remember, work is equal to force times distance. Just like distance is rate times time here. So if this were distance and this were work, this were the force being done, then the area underneath the graph would actually represent work. And so there's a lot of different applications of this idea here. So we're getting to some really neat things here. So in the next section, we're going to learn how, at least in some simple cases, you can take the limit. You can get an expression, a closed form expression of the finite sum in terms of n, where n is the number of rectangles you use, and then you can let n go to infinity, and you can actually find the exact area. Now this only works for some real simple functions, but it's kind of neat to see. And then in the final video, we will see that we'll actually prove the fundamental theorem of calculus, and that's going to give us a tool for finding the area underneath any curve, as long as we know the antiderivative of the function forming the curve. Okay, because there is that connection between the area under the curve and antiderivatives.